Whether you're a beginner in FreeCAD or an experienced user, the focus is often on getting a model to look right. But the real challenge isn't creating the model, it's creating one that survives changes. This lesson delves into how history-based parametric CAD works, why models break, and how to design stable, reliable FreeCAD models that evolve without falling apart. If you're enjoying this channel and you want to support what I do, I have a Patreon page. You can pledge support only or choose a selected tier that includes early access to videos, downloadable written PDFs of tutorials, and some extra bonus content. If that sounds good to you, I left a link on screen and also in the description of these videos. All history-based CAD systems work on the following rules. Each feature consumes the result of the previous one. Each feature defines downstream topology. Changes propagate forward, not backwards. Early features are seen to be least volatile. As the chains or chains grow, there is an increased chance that changing something upstream can cause the model to go into error further downstream. Many parametric CAD systems warn against referencing downstream or late-stage geometry. This is not FreeCAD specific. You'll find the same guidance in SolidWorks, Creo, and Fusion 360. In this lesson, we'll learn about model stability by exploring the different methodologies used to design models and how to mitigate against the impact of changing early features. We'll also look at the process of repairing your models when changes cause problems. To understand what's happening, we have to venture into the world of topological naming. Let's take the following simple model, where the chosen construction method involves attaching features directly to faces. And let's see what happens when we delete an earlier feature. So we have the pad, the second pad, and the pocket. Now I don't want this feature here, which is this pad. Note when I click on the pad, all the volume is selected. If we hit delete on the keyboard, it's going to warn us that there is dependencies. So I'm just going to hit no. If we look inside the pocket, we have sketch 002. But these are nowhere near this feature, this hexagon pad. That feels counterintuitive at first. If we delete the pad or the hexagon and hit delete and select yes to the warnings and make the pocket visible, the sketch is left behind, which we can remove, but the pocket still remains. So what is the problem here? All sketches will show the geometry, in this case the face, is attached to, and the attachment method. The pocket still has the attachment mode, but it has no support, as it's been deleted. This is exactly what the object dependency warned us about. If we look at the placement and the position, the Y has a value within here. So the sketch is relying on the placement, where before it was taking the attachment values. When a sketch is attached, the placement is updated. The same if the attachment offset is set. The placement adjusts automatically as well. This is basically acting as a fallback. Why does removing a hexagon pad affect the whole that wasn't even created on it? The same thing happens in any history-based parametric CAD system. To understand why, we need to walk through how the model was built. We first started by creating a base feature. From a sketch, attach the base plane. From there, a pad was added, our first feature in the tree. Inside the body, we have a feature tree. If we ignore the downstream features and just concentrate on this one, at this point the model has a single state. And if we hover over the top face and look down to the bottom left, we can see that we've pre-selected pad face 6. We can also see this in 1.1 and upwards with a long left click. And we get the clarify selection. We see the object's the pad and the face is pad face 6. The next stage, we selected the top face and created our next feature upon it. Now if I show the sketch, we can see the hexagon on there. If we look at that sketch, its attachment support is pad face 6, this one here. When the operation is run against the sketch, a pad is created. Now if we look at the same face, this one here, and look down to the bottom left, we see a change. We see that the same face is pad 001 face 5, not pad face 6. The feature is just not the hexagon pad, it's the whole volume. It's basically like a geometric skin that's been placed upon the top. The operation creates a new feature that's the shape of the profile but envelopes the whole model. We see this with the pocket. If we look at the sketch, which is on the side, the sketch is attached to pad 001 face 3, so the previous feature that's created by the operation. The pocket is created, last operation, and if we click the pocket, notice the whole lot is highlighted. So really, this is not the feature, the whole lot is. We can see that when we hover over the same face, we see that the face name, if we look to the bottom left, is pocket face 3. The last feature is called the tip. You can see that because the operation that created that feature has a white arrow. All other features are grayed out. These are moments in time showing the previous state of the model. Once you see your model as a sequence of complete historical states rather than a single evolving solid, this behavior starts to make sense, and it stops feeling like FreeCAD is being problematic, when in fact it's behaving exactly like history-based CAD systems should. Features are created sequentially. Each feature depends on a previous feature. Deleting or reordering earlier features may break later ones. Change and dimension upstream, all downstream features update. How can we remove the hexagon in this scenario without causing warnings or errors? One technique that is not often covered in this context, as it's quite new to FreeCAD, but it's used in other CAD packages, is suppression. Suppression is basically an on-off switch for a feature in the model history. When a feature is suppressed, it does not perform its operation. Instead, it simply passes through the result of the previous feature. The feature remains in the tree, but has no effect on the model. Suppressing a feature can, in some cases, be used as an alternative to deleting the feature, or as a way to plan a deletion in a more controlled manner. So with our model, let's have a look at the hexagon, which is created from this sketch. The sketch is attached to the previous feature, the pad, face 6, and the pocket is attached pad 001, face 3. So if I click on pad 001 and right click and suppress, if we look at the sketch for the pocket, it's still saying pad 001, face 3, but we see we need to recompute the feature tree. Let's hit refresh and watch the attachment support. It's now changed to face 2, but it still says pad 001. It's attached to pad 001, but pad 001 is suppressed. So in this case, the face in the same 3D space gets passed through. So if we look at the previous pad and show that, and hover over this face here, look down to the bottom left, it's saying face 2. So this is the same face as the attachment support pad 001 it's attached to, but it's occupying face 2 of the previous pad. If we look at the pocket now, it's been applied, just hide the sketch, and we suppressed pad 001. A good mental model to remember: early features should define the functional decisions, i.e. the intent. Later features decorate. For example, dress-up features such as fillets and chamfers should be applied as far down the feature tree as possible. In other words, near to the end. They change the topology and are at high risk of change by the designer, which increases TMP risk for everything that's downstream. If something defines the shape logic of the part, it should live early and be stable. The intent is the functional decision: size, precision, symmetry, interfaces, and clearances. Upstream is early in the model tree. These are base sketches, primary pads, layout sketches, and master dimensions. Downstream are the later features: holes, pockets, fillets, chamfers, patterns, and refinements. Some of these features and phrases you haven't been exposed to yet, but you'll get to know them in due time. Early features are often seen as stable because fewer operations depend on them, so their regeneration is more predictable. We have to be careful not to make assumptions here. An early feature could be an interface. Say a pattern of holes that fit into another part that's in assembly. This is in no way stable, but it's a design intent. What we should be looking at is to avoid anchoring to fragile features. A fragile feature, i.e. the last face of a pattern, can have the occurrences change, which can cause your model to break. Rather than suppressing this model, let's fix the issue. Let's unsuppress pad 001 and refresh. We have the pad back. So now I'm going to take pad 001, hit delete on the keyboard and select yes. I don't need the hexagon, we can get rid of that. We need to concentrate on the pocket and the sketch within. The attachment is missing, the map mode is flat face. That showed the previous operation, the pad, and showed the sketch of the pocket, the one we need to fix. Select the sketch and look at the attachment support. As we showed in the previous operation, the pad, we can select its face. Verify it by looking down to the left and we see we've got pad face 2. Come into the attachment support, click on it and use the button on the end. The link window will pop up and we can now select the face. We see that the pad face 2 has been selected. When we hit OK, we now have the attachment support of pad face 2. The sketch is showing that it needs recompute. We just refresh and now the pocket is attached correctly and we can hide the sketch. Another way is to remap the sketch. So rather than using the attachment support, we use the map mode. We delete the pad, come back to the pocket and select the sketch. If I hover over this face, at the moment we're still showing the pocket, so we need to show the pad, the feature that's going to be attached to. Now we come down to the map mode, select that and use the button on the end. The attachment panel will be shown. A reference, it's saying selecting. If not, we just click it. We see our sketch and we select face. Now attach plain face to pad face 2. We hit OK, we refresh and then show the last operation. We can now get rid of the sketch for the hexagon. The sketch is now mapped correctly to the right face with the right map mode. The feature chaining workflow is a modeling approach where each new feature is built directly on the result of the previous one. A typical chain might look like this. In this workflow, each sketch is attached to the face created by the immediate preceding feature. This creates a clear linear chain of dependencies where every step builds directly on the last. At first glance, this approach is often criticized because it relies heavily on generated faces, which can be fragile in complex or frequently changing models. However, this misses an important factor, the design intent. If the goal is to model something simple or self-contained, feature chaining can be valid and also the better workflow. These parts are usually designed sequentially, where each feature exists because of the one before it. In that context, attaching sketches directly to faces reflects how the part is actually being designed. Trying to force a more complex workflow onto every model can add unneeded work and make it over-complex, especially when we realize we're not building an F1 engine block, it's a wall bracket. The key takeaway is that intent matters. Feature chaining is fragile when intent is unclear. Attachment is to fragile features or is applied when large design changes are expected. But when the intent is simple, local and linear, chaining is perfectly reasonable and often is the more efficient workflow. If you need to reference geometry, it may be more beneficial to attach your features to the earliest possible feature in the tree. Doing so makes it less fragile and helps prevent later features from breaking when the model evolves. We end up creating multiple chains, all starting from the same feature, resulting in better stability. Care must be taken not to overload the feature. In this example, we have the start of a hinged box, yet to be hollowed out. On the left-hand side, you can see we have a linear pattern. This is an unstable feature. Let's say I want to place a sketch upon this face. Creating a sketch after selecting the face, and then creating, say, a circle. I want this centered on this face. So we use the external projection tool, and instead of pulling in the 2 points, let's say we pulled in these 2 lines. These lines are unstable because they're affected by the linear pattern. If these were just 2 points, they would be fine. I'm going to right click to cancel the tool and take the 2 points and the center of the circle and use the symmetry constraint. Let's close now. And we'll just add a pad upon there. Let's come back to the sketch and see what happens when we start changing some dimensions. Note the lines that have been pulled in are in purple, and they're broken lines, so they're dashed lines for the construction geometry. Come over to the model and look at the original pad, this one here, that creates the box. Inside I have a sketch. Let's just show the linear pattern. So our sketch, look down to the constraints. I can change the constraints within here and change the width of the box, say to 25, and click off. We see that everything's okay. And the circle stays in the middle. But what happens if I change the linear pattern? The occurrences at the moment at 5. Let's change this to 4 and click off. We have one less occurrence. You notice that the line now has changed from purple to orange, showing it's broken. We come back into our original pad sketch, look at the constraints, and change the constraint to 25 and click off. The external geometry has changed, but it hasn't conformed to the rest of the shape. Changing the linear pattern has broken the geometry. So how do we get around this? Let's close this, and I'm going to delete the pad and the sketch. And this time, instead of attaching to this face, I'm going to move up the chain to a stable feature, the pad. Select the face and create a sketch upon it. We'll bring in the 2 points. Same again, let's just bring in the lines as we did before. Add the circle. And then take 2 corner points and the center to make that symmetrical. And hit close. So our linear pattern, our tip, has not been attached to. So I can take the sketch and create a pad. And now when I change the linear pattern, this won't affect the pad. We can see that, go into the sketch. You can see that the operation that is attached to has been shown. So changing the original sketch of that pad, the original sketch to change the dimension of the box, we're all fine. And then to change the linear pattern, and we won't see that because we need to show the linear pattern. Everything is working fine because the attachment is not to the linear pattern, but to the pad itself. Another way of improving the chaining approach is to prefer sketch geometry, such as lines and points, rather than the faces or the edges of the created solid. Sketch geometry is stable and predictable, making it a more reliable foundation for downstream features. With this method, we can still add a sketch to the linear pattern. But instead of referencing the edges, we come back to an earlier feature and show the sketch. Hide in the linear pattern and pull in the references from the sketch. Now, because this is centered, we would use the centered line. But if we create some construction geometry and attach it to the center point, and then center the geometry, making sure we have construction geometry. If our pad sketch, the attachment of which changes position, then our sketch will follow. We're still required to add a dimension in here. When we come back and close, our circle is positioned in the center, even though the sketch has moved position. And if we change the linear pattern, change the occurrences, say 3, our sketch is still stable. Because it's referencing a stable pad sketch, rather than the fragile edges of the geometry generated from the pattern. The following approaches focus on building models on a more stable foundation, starting with a stable reference and progressing to master sketches, which capture the essential geometry and design intent. We'll look at such methods as referencing the origin directly, the master sketch workflow, tips on using ShapeBinders and using expressions, varsets, and spreadsheets. One way to improve model stability is to be deliberate about what you attach the sketches and features to. Choosing a stable reference early reduces the downstream issues. Attach sketches and data and objects to the body's origin planes and axes. These references are permanent, and their identification never changes. When positioning is needed, use attachment offsets. Favour this rather than attaching it directly to the face of the previous feature. When we create a body in the part design, the origin is placed within. When we create a new sketch, the origin becomes visible, and we can attach to the planes. So our first attachment is always stable. After we run an operation against the sketch, let's say just a simple pad, then if we was using feature chaining, we just attach the next sketch to the faces. Reference the origin plane directly, we make sure nothing's selected, so when the next sketch is added, it's placed on one of the planes. Let's say I want to place a feature on this face, but I'm going to use the origin plane. Let's pick the YZ plane. Trouble is, the sketch is in the YZ plane rather than sitting on the face, so we need to add an offset. If we look at the sketch, we can then open up the attachment offset, the position, and move the sketch so it sits upon the face. So for this one, be at 38mm. I can then sketch with reference to the origin point and not reference any of the edges by using the external geometry. This workflow can be quite time consuming, but it creates a more stable workflow. The sketch origin can be referenced, and so can the axes. Once we've finished sketching with reference to the origin and the base plane, we can close the sketch and then run our operation. We must be mindful of the operations we run as well. Such operations as up to face means that we're referencing the generated geometry. So we have to make sure our operations are compatible. As you can see, it's a longer workflow, but it creates a more stable model. The trouble is, because we haven't referenced any faces, if we change the dimensions, then the sketches that have been positioned will end up hovering in 3D space. And for example, if this pocket was a set dimension pocketing inwards, then we need to take into account the size of the pad and apply that to the attachment offset. And this is where expressions can help us. A common and effective way to work around reference stability is to use one or more master sketches. These are simple sketches created early in the model. They define the core geometry and key dimensions of the part. Things like the overall outline, main profiles, hole position, and critical spacing. The master sketch should be placed as the first feature in the body, or even outside the body for maximum flexibility. It should remain intentionally minimal, only the geometry that's needed to describe the design intent with clearly named constraints that are easy to reference later. Later sketches and features reference the master sketch, either through external geometry or binders, instead of referencing faces or edges created by solids. This approach works because the master sketch is created before any solid geometry exists, and is typically attached to a stable reference, like the origin planes and axes. Since those references never change, the master sketch remains valid, even when the model is heavily modified. Downstream features inherit that stability. When dimensions or layout changes, the updates propagate cleanly throughout the model, without breaking face or edge references. In practice, this shifts dependencies away from fragile topology and back onto explicit internal geometry. In short, the master sketch acts as a single source of truth for the design. As long as it remains stable, the rest of the model can evolve around it with far fewer failures, making it one of the most reliable ways to avoid topological naming issues. When it comes to ShapeBinders, we have to be careful. They work best when used to reference stable geometry, such as the master sketch outside a body or from existing sketches. Creating binders from faces or edges of a generated solid can inherit the same fragility that causes the topological naming problem. Keep in mind that if the source sketch geometry is deleted or heavily edited, binders can break as well. If using a sketch, it's best to bind the whole sketch rather than just an edge or a face, as the changes will propagate to the shape binder as well. For best results, only bind to geometry you know will remain stable throughout the modeling process. Instead of hard-coding numbers directly into sketches, it's often helpful to drive dimensions using expressions, spreadsheets, or varsets. This approach reduces direct dependencies between features, making the model more flexible and easier to modify. If a key dimension changes, updates will automatically propagate without breaking the downstream features. If we remember back when we created a body and a sketch upon the base plane, let's create a simple rectangle, and we set some parameters in here. Then when we take this and pad it, we'll keep the 10mm. If we map the sketch to the face, then as the pad increases, the sketch will follow. But if we're placing directly onto the base planes, in this example the XY plane, then we need to offset the sketch because it's directly on that plane. That is done through the attachment offset. It'll be the same height as the pad, but if the pad is increased, let's say by 12mm, then any operation applied to that sketch will now be inside the body. To save us going back to the sketch and changing the attachment offset to the length of the pad, we can link these using expressions. If I click on the field, we get the expression icon. We can click the expression and type in the ID of the pad, which in this case is just pad. As you can see here, this is the label. So if we rename this pad, we can use the name in chevrons. We select the pad, we then have a length, and we can hit OK. We've now connected the position of the sketch along the Z, the normal, to that of the pad length using an expression. So if I change the pad and set the length back to 10, the sketch follows as well. We can also drive this from a data source, such as a spreadsheet or a varset. Let's add a varset using the icon on the toolbar. This is a name value pair. So I can give it a name, say pad height. I can define a group where it's going to sit. This will be the group in the properties. I'm just going to leave it in the base. And the type, I can set property length. And its value, we'll just give it a random value. Let's say 5 and add it. We can add other parameters. If we hit close, we see the varset on the left and we have the pad height. Now if I click on my pad and look at the length, we can use the expression on the end and set this to varset dot pad height and hit OK. We're driving the pad from the varset. As the sketch attachment position is linked to the pad length, as you can see there, any alterations to the varset will update the pad and therefore update the sketch position. To make this more clearer, I'm going to set this to the varset as well. So varset, if we don't have a list of parameters, we just delete the dot and add the dot again, and we'll select pad height and hit OK. Already on the right, you can see it's updated. So now we control the parameters via the varset. Let's make this 12 and hit enter. Therefore, our model becomes much more parametric and much more flexible. FreeCAD 1.0 and above has significantly improved the handling of the topological naming problems. With better heuristics and fewer silent failures, we still have to be careful of what we attach to. Applying these techniques ensures that your parts remain flexible, reliable, and easier to maintain, especially as your design grows. But always remember the design intent. We could spend a lifetime creating the perfect, failure-proof model of a simple wall bracket. If you like what you see and you want to donate to the channel, then you can do so via Ko-Fi or Coffee at ko-fi.com/MANG0 or via PayPal at paypal.com/paypalme/DarrenBEstone. I also run a Patreon where you can get early access and additional content, and that's at patreon.com/MangoJellySolutions. Links can be found in the channel header, on the About page, or in the descriptions of these videos. I thank everybody that's donated so far. It really helps to keep the lights on so I can produce more content and also expand the channel. Thank you for liking, commenting and subscribing to these videos, and I hope to see you again in the next one.